So we're looking at trigonometric identities, showing identities are true or false. So for instance, we've seen some trigonometric identities before. For instance, we saw the Pythagorean trigonometric identity, sine squared theta plus cosine squared theta is equal to 1. We talked about you can derive the two other forms of the trigonometric identity by either dividing everything through by sine squared. And so let's think about it. If you divided everything through by sine squared, this first term, sine squared over sine squared, is 1. Plus, we would have a cosine squared theta over a sine squared theta. Well, cosine over sine, which is another identity, that one is cotangent squared theta, is equal to 1 over sine squared theta. It's an equation. And so 1 over sine is cosecant squared theta. Oops. So we can cover or get the other identity by dividing everything through by cosine squared from the one that we should have memorized. So sine squared over cosine squared, that's tangent squared theta, plus cosine squared over cosine squared is 1, is equal to 1 over cosine squared, which is the secant squared theta. So these you should be able to recognize. And so sometimes just, I know that the sine squared plus cosine squared equals 1 or any form of that, or I can try to recognize that, or recognizing the other. So I might, if I know I'm trying to prove trig identities or I might be using them, I might have these in front of me when I'm doing these problems. So the other things that you guys should remember, and hopefully you do, and I was saying it while we were doing this, was that tangent theta was the same thing as sine theta over cosine theta. That cotangent theta, that's the same thing as cosine theta over sine theta. Secant theta, that was the 1 over cosine theta. And cosecant theta, that was the 1 over sine theta. And so we also discussed that a lot of times if we know cosine and sine at values, then we can figure out the other ones because all of our other trigonometric functions are in terms of sine and cosine. So those were the most important ones to definitely memorize with your special angles and quadrantal angles. The other things that we looked at that are going to be helpful while we're proving these identities are the functions are even or odd. So if we look at cosine of a negative angle, theta, cosine, this was a even function. And so this was the same thing as if you looked at just cosine of theta. Sine of theta, or sine of negative theta, sine is a odd function, and so sine of negative theta is the same thing you would get if you evaluated it negative sine of the positive of that angle, theta. Cosine, let's see, tangent theta, or negative theta. Well, if we broke it down as sine of negative theta over cosine of negative theta and use these rules, this would be negative sine of theta over cosine of theta, and that gives us a negative tangent theta. And so reciprocal of cosine, that one is secant. So if we look at secant of negative theta, this is the same thing as 1 over cosine of negative theta, which is positive. And so this is the same thing as secant of positive theta. Cosecant of negative theta. Again, that's 1 over sine of negative theta, but sine of negative theta is the same as negative sine of theta. So 1 over negative sine of theta is the same thing as negative cosecant of theta. And then last but not least, cotangent of negative theta is the same thing as negative tangent of theta. And that's just the reciprocal. Cotangent of negative theta is the reciprocal So that would be 1 over negative tangent of theta, which is negative tangent of theta. Okay, so we are going to use these identities that we know or are given, and we've kind of showed before that are true, and we got them, to prove other identities. So working with identities are different than working with equations. So working with equations, we can move things on both sides of our equation back and forth to manipulate it. When we're solving identities, we don't want to do that. We only want to work on one side of the equation of the identity, and the goal is to get it to look like the other side. When you're looking at the identity that you're trying to prove, you're always going for the most difficult side is usually the one that you want to work on to make it look more like the simplified side. And so there's certain tricks, and they're recognizing some of these identities. Those are helpful. If you have multiple fractions, rewriting it as a single fraction could be helpful. Rewriting things in terms of just sine and cosine can be helpful. So I'll kind of go through some examples and I'll just kind of show you the tricks. The thing is, with these identities, you just got to start somewhere, and you just got to just start playing with it. So you'll notice that sometimes you're going to start somewhere and it's just getting you nowhere. And you'll notice that it's just getting messier and it's just not working. And so you got to go back and then try something different. So it's possible that when I start one of these equations or identities to show that I might go off on a wrong tangent. Not literally tangent. Okay. So let's look.
Is this the beginning of 8.4?
4, yeah.
Okay, got it. Thanks.
So let's say it says establish each identity. Other books, I usually say prove. So cosine theta, all times cotangent theta plus tangent theta. We want to show that this is equal to secant theta. Okay, so you look at it and then you choose which one looks more difficult. Well, obviously the left-hand side of the equation looks more difficult. And so we're only going to work on the left-hand side of the equation. And our whole goal is to get this left-hand side of the equation to look like the right. And so when you're working with this, identify which side of the identity that you're going to show looks like the other. And so I'm going to say, I'm going to work on the left side. And so looking at the left-hand side, I want to manipulate it to look like secant theta, and sometimes these fall out right away, and so hopefully they do. Let's rewrite cotangent theta and tangent theta in terms of sine and cosine. And so, I mean, there's multiple ways we can start this. So cotangent of theta, well, that one is cosine of theta all over sine of theta. Plus tangent of theta, that's the one sine theta all over cosine of theta. So I can rewrite this as a single fraction inside of my inside my main parentheses, or I can start by distributing. And so it doesn't matter which way you go. At the end, we should get the same result. So if you distribute to both pieces, notice that when we distribute to the sine theta to cosine theta over sine theta, those sine thetas cancel, and you're just left with a numerator of cosine theta. Plus, this time though, when we distribute sine theta to sine theta over cosine theta, nothing cancels, and so we're left with sine squared theta all over cosine theta. Okay, so this is where rewriting this as a single fraction is helpful. And so in order to rewrite something as a single fraction, we need a common denominator. And so our least common denominator is cosine theta. And so we're going to multiply cosine theta by a fancy one, cosine theta over cosine theta. So this gives us cosine squared theta in the numerator there, all over cosine theta. Plus sine squared theta, all over cosine theta. Well, cosine squared plus sine squared, if you don't recognize that, hopefully you do, all over our denominator of cosine theta. But by our identity, cosine squared plus sine squared is just 1. 1 over cosine theta. This is equal to secant theta. Okay. So we just got to what we wanted to show. We got to the right-hand side. We only worked with the left-hand side while we were doing this. So when you get further in math, I think they still do this. When you're done with a proof, you put a little square after it. And that says that you're done with that proof and you showed what you wanted to show. I was just seeing if you looked at it. I don't see it. Okay, so it's kind of a game, puzzle, trying to figure out, take something that's kind of complicated and get it and manipulate it to what you want. So what about 1 minus cosine squared theta all times 1 plus cotangent squared theta. This is equal to 1. Okay, so I'm going to work with a more complicated looking side, which is obviously the left-hand side. So working on the left-hand side. So I notice I can either rewrite cotangent squared theta right now as a single or as in terms of sine and cosine, or I can first distribute. Just to save time with not having to rewrite this as 2 trig functions, let's first distribute, and then if we need to, we can rewrite that in terms of sine and cosine to simplify. So if I distribute, I'm looking at 1 times 1, so that gives me 1. 1 times cotangent squared of theta, so this is plus cotangent squared theta. Now distribute our negative cosine squared theta. So negative cosine squared theta times 1 is negative cosine squared theta. And negative cosine squared theta times positive cotangent squared theta. So this is minus cosine squared theta, cotangent squared theta. So if you don't mind, let's actually, okay, cotangent squared theta. So let's, oh, I see. I think I might see, I'm not sure. No, I was gonna go backwards. I was gonna factor it. I was like, oh, I see things we can factor out, but no, that's stupid. That would be going back to what I just did. So let's try maybe rewriting this cotangent squared in terms of sine and cosine. And so let's do this. We have 1 plus cotangent squared. Theta is cosine squared theta over sine squared theta.
Professor?
Yes.
I think there's something going on with the audio.
Oh, no.
I'm good on my end, but I don't think. Yeah.
No, your audio is fine. It's just the fact that some people are hearing a weird squealing noise coming from your audio. It's not too distracting, but it's very slight. I think people are just just complaining about it. I don't know.
Yeah. Hold on, let me see.
I hear like the traffic going by. I think
Okay.
someone has their mic on.
Let me just mute all. Let's see if that helps. Allow participants. Okay. Is that sounding better? I was hearing what sounded kind of like the traffic, but well, now you guys can. Now that I unmuted you all, you can't respond. Okay. Okay, so let's see if that works. Okay, good. Okay, so let's continue just rewriting this expression, this left-hand side, in terms of just sine and cosine. And so we have minus cosine squared theta, minus cosine squared theta, and then cotangent squared theta. This again is cosine squared theta over sine squared theta. Notice that nothing is going to cancel here. I don't like that. So next thing I probably would do is get a common denominator. So our common denominator, well, that's just sine squared theta actually. So our LCD is sine squared theta. So if I multiply our LCD, sine squared theta over sine squared theta times 1. I'm sorry, sine squared theta over sine squared theta is 1. Then we have this plus. Well, that already has our denominator there. So plus cosine squared theta over sine squared theta minus, so this does not have our common denominator, and so multiply the negative cosine squared theta by sine squared theta over sine squared theta. So we have cosine squared theta, sine squared theta, all over sine squared theta. And then this already has our common denominator, but let's just multiply sine squared theta times sine squared theta. So sine squared times sine squared, well, that's sine to the, I'm sorry, it's cosine squared times cosine squared. So that's cosine to the 4th power theta over sine squared theta. Okay, so we can now rewrite this as a single fraction all over our sine squared. So we have this sine squared theta plus cosine squared theta. And then we have this minus cosine squared theta, sine squared theta, minus cosine to the 4th theta. Okay, so some red flags come out because I have a sine squared plus a cosine squared. And I know that this is equal to 1. So let's rewrite that as 1. But notice that the last 2 terms in the numerator, I notice that we can pull out a cosine squared. And if we pull out a cosine squared, and maybe I should have left this cosine to the 4th theta as a cosine squared times cosine squared, I notice I'm also going to have something that looks almost like our Pythagorean identity. So let's actually pull out a negative cosine squared. So if I pull out a negative cosine squared, we're going to be left with the first term, we're going to be left with a sine squared theta. Plus, and then if I pull out a cosine squared from a cosine to the fourth, I'm also left with a cosine squared theta. This is all over sine squared theta. Okay, so I know that sine squared theta plus cosine squared theta, again, using that trig identity, we know that this is one Pythagorean identity. So remembering your goal, what you're trying to get to, our eye is on manipulating this to look like 1. And so my numerator now, with simplifying, rewriting things, is 1 minus cosine squared theta. This cosine squared theta times 1 is 1, or cosine squared theta, all over sine squared theta. We're trying to make this look like 1. And so, like I was saying, being able to identify other forms are really helpful. Well, cosine squared theta plus sine squared theta equals 1. If you subtract cosine squared theta on both sides, that would say sine squared theta is the same thing as 1 minus cosine squared theta. So we have sine squared theta over sine squared theta. And we got what we wanted. We manipulated that to be 1. So sometimes putting your reasoning in there is helpful of why you jumped from one place to another, especially on an exam that will help with getting extra credit or partial credit.
And then that's the final answer to that
Yeah.
equation? Okay.
Yes. So you're not done unless you can manipulate this one side that you're working on to look like the other side.
So on that,
yeah, Elizabeth, I'm sorry.
sorry. So on that really long step, so after the purple with the blue red, how did you condense that down to the 1 minus cosine squared in parentheses? I lost right there.
Okay, so that part right here, we have cosine squared. You got how that we got sine squared plus cosine squared, that's just 1. And so we just replaced this with 1 right here. That's where we got the 1. So right here, the negative cosine squared sine squared theta minus cosine to the 4th theta, those both have cosine squared theta in common. So all I'm doing is I'm pulling out a negative cosine squared theta from both of those terms. And so if you pulled out a negative cosine squared theta from this piece, all you're left with is that positive sine squared theta. And if we pulled out 2 negative cosine thetas from 4 of them, then you're left with a positive cosine theta, squared theta.
Okay, got it.
But that also is 1. And so when you take that red negative cosine squared theta times this 1, it's just that we have that 1 that we brought down from the other cosine squared plus cosine squared minus this. And then this is where just identifying that identity using that sine squared theta plus cosine squared theta equals 1. And if you subtract both sides by cosine squared theta, that's just a side note, then you have sine squared is the same thing as 1 minus cosine squared. So we can just substitute that in. And so really on all of these, you know your goal. So you know the answer. You know these are telling you these are identities, prove that they're true. And you're using other identities, the main ones that you should know, to manipulate it to look like it. And so a lot of these, and maybe this is why I like them so much, is a lot of it has to do with using algebra to do that. So let's prove cosecant u minus cotangent u is equal to sine u all over 1 plus cosine u. Okay, so this one, it doesn't really matter what side you work with. I can see, if I worked with the right-hand side, sometimes it's helpful when you have fractions multiplying by the conjugate of the sum of two terms. So this 1 plus cosine u, if I multiply both the numerator and denominator by the conjugate, 1 minus cosine u, that can help us get our trig identities that cosine squared plus sine squared equals 1. So we can do that, or we can work on the left-hand side and we can rewrite this as in terms of sines and cosines and try to get a fraction. So it really doesn't matter because one doesn't look more simple than the other. Or I'm going to go with working with the right. So let's work with the right-hand side. Okay, so let's try multiplying this by a fancy 1. And this is going to be something that you use over and over again, especially in calculus, to help you manipulate things, multiplying things by the conjugate. And so let's multiply both this by 1 minus cosine of u all over 1 minus cosine of u. So we're changing it, but it's equivalent because this is just 1. So let's maybe distribute our sine of u, or maybe not. Let's, I don't know. So sometimes, like I said, you just got to go and you got to work with it. So maybe let's distribute that sine u. So we get sine of u times 1 is sine of u, minus sine u times cosine of u. So minus sine u cosine of u. This is a difference of squares. So basically, this is in the form of a squared minus b squared is a plus b times a minus b. So if we just square the first term, we get 1 minus squaring the second term. So cosine u times cosine u is cosine squared u. I should not have distributed, I don't think. Because notice that we can rewrite this as a single term, I think. Let's pull out the sine u on top for a minute. 1 minus cosine of u. And let's use our identity here. Let's rewrite sine in terms, or cosine in terms of sine. And we can do this because it's a square. I could not do that if it was just 1 minus cosine u. But we know again that sine squared u plus cosine squared u, let me just write it over here, equals 1. So if I want to rewrite cosine squared u in terms of sine, I would subtract sine squared on both sides. So cosine squared u is equal to 1 minus sine squared u. So let's rewrite that, put that in here. So instead of cosine squared u, we're going to rewrite it with our other form of our Pythagorean identity, 1 minus sine squared u. So we got to distribute that negative outside the parentheses once we had rewritten cosine squared u to inside the parentheses. So we have sine u in the numerator times the quantity 1 minus cosine u all over 1. We'll distribute in the negative. I get minus 1 plus sine squared u. Notice our ones cancel. So sine u all times 1 minus cosine u all over sine squared u. So notice you have its multiplication on top between sine u times this parentheses. There's no addition outside. We can simplify. We have a single sine u on top and we have 2 of them on the bottom. So cancel the sine u on top, get rid of one of them on the bottom. We'll notice that there's 2 terms here. Now we just have a fraction. So it's helpful to go backwards. So we have 1 minus cosine u right now all over sine u. A lot of times we're trying to get multiple fractions as a single fraction, but it's also helpful to go from a single fraction to multiple fractions. So we can do that. We rewrite each term in the numerator over the denominator. So this would give me 1 over sine u minus cosine u over sine u. And I believe we're almost there because we're trying to get it to look like cosecant u minus cotangent u. And 1 over sine is cosecant. So this is cosecant u minus, and cosine u over sine u is cotangent u, which is what we wanted. And so we're done. Okay, so last week we were working with equations. So again, I was saying equations and identities are different. These identities we're just trying to manipulate on one side and make it look like the other. The equations, we were doing things to both sides of our equation to get our variable by ourselves or to be able to solve for our variable. And so one of the most common errors students make on this section is moving things to both sides, and that's not going to work. So this is all this section is going through and kind of manipulating. So let's see. How about 1 plus sine theta all over 1 minus sine theta minus, then we have a new fraction, 1 minus sine theta in the numerator all over 1 plus sine theta. And we're trying to manipulate this, or we're trying to manipulate the other side. 4 tangent, it's equal to 4 tangent theta times secant theta. So this is where you got to determine which one you want to work with. I'm thinking the left might be better because if I'm working with tangent and secant and I rewrite those, I'm thinking I'm not going to have a hard time manipulating my denominators. Maybe not, I don't know. But the left-hand side looks a little more difficult. And so let's work there. So we can combine that as a single fraction. And noticing this, my LCD at the left-hand side is 1 minus sine theta all times 1 plus sine theta. Okay, so we have our LCD is equal to 1 minus sine theta all times 1 plus sine theta.
Professor, I have a question.
Yes.
How do you determine the lowest common denominator for these?
So the smallest thing that they both divide into, and so since this has 2 terms in it and this has 2 terms in it and they're not identical and they can't be factored, we need each denominator as our LCD. Does that make sense? So
Yeah, it does.
Okay. Yeah, so that would be like the same as if this was 1 minus x and 1 plus x. The common denominator would be both of them. So let's just rewrite it because we know that when we're combining and getting the LCD that we're going to put it over that common LCD, right? 1 minus sine theta all times 1 plus sine theta. And then we have the piece that is missing that we would have gotten the LCD times this numerator. Well, we were missing the 1 plus sine theta. So we have the 1 plus sine theta that we multiplied this fraction by to get our LCD times the numerator, 1 plus sine theta, minus, and then we have our numerator here, the 1 minus sine theta, times what we needed to multiply that by to get the LCD. Well, what we needed to get the LCD, we were missing the 1 minus sine theta for the second fraction, and so we needed to multiply that by the 1 minus sine theta. So let's distribute, and I think things are going to start canceling out really nicely, and I would distribute both in the numerator and denominator. This is basically 1 plus sine theta times 1 plus sine theta. You can, if you remember the formula, you can apply it. It's a sum of 2 terms squared, or just distribute. So we have 1 times 1 is 1. We have 1 times sine theta, that's a sine theta, but we're also going to have a 1 times sine theta, which is another sine theta. So sine theta plus sine theta, our 2 middle terms are 2 sine theta. And then I have a sine theta times a sine theta, that's sine squared theta. Don't forget that minus, and so we need to make sure that negative later is going to be distributed. But multiplying out 1 minus sine theta times 1 minus sine theta, that gives us 1 times 1 is 1. I'm going to put parentheses here so I don't forget. So here's a negative sine theta, and we're also going to have a negative sine theta. So negative 1 sine theta minus 1 sine theta is negative 2 sine theta, the 2 middle terms. And then negative sine theta times negative sine theta is positive sine squared theta. All over. So our denominator is basically a difference of squares. So if we just square our first term, which is 1, I don't know if we should do it now or later. I guess we could go, I guess we can do it now. I always tend to be wrong. So 1 plus sine theta minus sine theta, middle term cancels, minus sine squared theta. Okay. think that's good. Let's distribute the negative, and then we can combine like terms. And so bringing down the first three terms that were not with a negative, we have 1 plus 2 sine theta plus sine squared theta. Distributing in the negative, we have negative times 1 is negative 1, negative times negative, so plus 2 sine theta. And negative times positive is negative, so sine squared theta. All over, right there, 1 minus sine squared theta. Let's rewrite that. This right here is the same thing as cosine squared theta. So let's put over cosine squared theta. And so notice things start to cancel. We got a 1 minus a 1, that cancels. We have a sine squared theta minus a sine squared theta, that cancels. And we have a 2 sine theta plus a 2 sine theta. Those are like terms. And so a 2 sine theta plus a 2 sine theta is a 4 sine theta. All over our denominator of cosine squared theta. And our whole goal is to get 4 tan theta secant theta. Let's break that down. Cosine squared theta is the same thing as cosine theta times cosine theta. And so we can break that up as a multiplication of 2 fractions, and then we can manipulate it to look like tangent and secant. So we have 4 sine theta. Let's put that over one of the cosine thetas. All times, well, we need a cosine squared theta again, 1 over cosine theta. So that would get us back up above. And now we know sine theta over cosine theta, well, that's just tangent theta. So we have 4 in front, a tangent theta. And then 1 over cosine theta is secant theta. Okay, so one thing that I don't I love my math lab and I love homework online, but sometimes it's hard because it's hard to justify how you're doing proofs. And so I don't really like how you want to try to work these out and then look, because I believe they have the A, B, C, D, and you're kind of looking at it and seeing it, which one looks correct and the reasoning behind it. But you should be able to come up with a reasoning behind this. Just see one other thing. Okay, so we're just kind of going to review quickly over inverse functions. And so we had to limit the domain on our trig functions in order for them to be a one-to-one function, and so that an inverse would exist. And so when you're having these equations or expressions that you're starting with inverses with them, in them, you have to be careful of that. Later, we got into solving equations, and when we were solving those equations, sometimes we used inverses to help us solve it. That we were looking though at solutions more than what we had bounded in order for sometimes the inverse function itself. So just kind of be cognizant of that. So if you had, for instance, sine inverse of negative root 2 over 2. And so I have to think about sine inverse and the domain for sine inverse is between negative pi halves and pi halves. or sorry, the range. Oops, and this is sine theta. I guess I can say theta. Okay, so I have to think about where sine is negative. I know sine is negative in here on the fourth quadrant between negative pi halves and theta. And so I think to myself first, what value sine gives me positive root 2 over 2, which I know is pi fourths, but I need to get down to the fourth quadrant. And in order to be it written like this, I'm going to do the negative of that angle. So negative pi fourths.
Isn't sine also negative in the third quadrant?
It is, but if you're talking about just sine, and so that's where I was saying you need to be careful. If we're solving equations, then you would have to consider that also the third quadrant as your answer. But because we're starting with this, we are given that in order for it to be a one-to-one function and for sine inverse to exist, it has to be bounded between these values. And if you look at the graph of sine inverse, if you kind of remember it, it looks like this, and this is where it's one-to-one. If I start to come down here, this makes it not one-to-one anymore. And so that's why they limit it between negative pi halves and pi halves, be able to get all of the range in there. I mean, they could have shifted it over and done that, and this would have came back up here. And so this was for sine theta. But cosine theta, if you look at the graph of that one started at the max and then it came down. And so it doesn't start repeating itself until you hit pi. Then it's going to come back up here. It's no longer one-to-one. And so that's why we limit cosine inverse between 0 and pi. Same sort of reasoning with the other trig functions. You have to make it so that the original trig function is a one-to-one function and have it between those bounds. And so,
excuse me, Professor.
Mm-hmm.
Sorry, I had a quick question. So, could we also do this problem by using like a triangle? So we could like draw a triangle in the fourth quadrant and then put the angle in, and then the opposite would be the negative root 2, and then the hypotenuse would be 2. And then we could use like a special right triangle to find the angle.
Yeah, so that's basically what you're doing, because you're kind of thinking backwards. You're trying to think what is the angle that would get us that. Normally, I wouldn't make that triangle if it unless it was a ratio of something I did not know. But you should know that sine of what gives you back root 2 over 2. But you're right about being able to write a triangle. I don't know how writing the triangle in this case would help me with the figuring out the angle though. For instance, so let me see. So let's look at one like this. So this is one I don't know the angle. So let's say we have secant of cosine inverse of negative 3/4. So I first think to myself positive. So I think to myself, is there any special angle of cosine that would give me back positive 3/4? And there isn't. The only ones I know are 1/2, root 2 over 2, and root 3 over 2. And so that's not one of the special angles. And so this is where I would create my triangle. We have to think about though when cosine is negative, because that's where my angle has to be, because I'm dealing with a cosine inverse. And so notice that cosine inverse or cosine is negative in between pi halves and pi. It falls below the x-axis here. So I know that theta in my answer has to be between negative pi halves and pi. And sorry, not negative pi halves, positive pi halves. So I want to create a triangle. And so I know, let's call, and it doesn't matter, theta is equal to cosine inverse of -3/4. So if we take the cosine of both sides of this, well, cosine of cosine inverse is just the argument, in this case, -3/4. So we're looking at cosine of the angle theta equals cosine of cosine inverse of -3/4. So we know cosine theta then is equal to -3/4. So create your triangle. I mean, I'm not writing this that it's in the how it looked like if I had put it up here. It'd be more like this. Okay. But I know cosine, the ratio, it's adjacent over hypotenuse. So looking at my theta, my adjacent side is down on the bottom. My hypotenuse is always across the right angle. This is where I'm not going to put in the negative, but I'm going to remember that theta is in quadrant 2. So I need to figure out the missing side of our triangle. And so this is a missing leg. So I know the missing leg is the same thing as, maybe we can call it y if we want. So y squared is equal to the square root of, well, get rid of the y squared if I'm going to put the square root. So y is equal to the square root of 4 squared, which is 16, minus 3 squared, which is 9. So y is equal to square root of 7. But we had called theta back above here to be what we're taking the secant of. So we can go in and we can replace cosine inverse of -3/4 with theta. So let's go back and rewrite this expression. So secant of that cosine inverse is the same thing as secant of theta. And so now we can use our triangle to figure out what secant of theta is. Well, secant, that's 1 over cosine. So actually, this one would have been okay. You actually didn't have to figure out that root 7. So it's 1 over cosine. And so the reciprocal, so that would be the adjacent, which is 3, all over the hypotenuse, which is 4. But we're in quadrant 2. And secant theta is less than 0 here. So we need that minus.
And Professor, wouldn't it be 4 over 3?
Oops, sorry, you're right. The reciprocal, hypotenuse over adjacent, 4/3. Okay, so I'm going to jump into 8.5, which is the sum and difference of 2 angles. We're going to look at that for cosine and sine.
Wait, so the answer was -4 over 3?
Yeah. Okay, so sum and difference of angles. Pull up that section. which again is 8.5. And so I'm going to prove to you why we can use these formulas. Just get there. So the sum and difference formulas for sine and cosine. Okay, so you need to remember that when you're on the unit circle, that your point is defined by either sine theta and cosine theta. So recall, on the unit circle, P at angle theta is cosine theta, cosine is your x value, comma, sine theta. Okay. So we are going to prove, and here's a theorem, first the difference of an angle for cosine. And from that one, we can derive the other ones. There's a theorem that says that the sum and difference formulas for cosine are the following. So if you have a difference of two angles, and we're going to call them the Greek letters alpha and beta. So alpha minus beta. So cosine of alpha minus beta, this is the same thing as cosine of alpha, cosine of beta, plus sine alpha, sine beta. Okay, so my goal right now is to prove that to you, why we can say that. But before we do that, let's just write out the the sum of two angles for cosine also. So cosine of alpha plus beta, this is equal to, it's almost identical as above. So, and I will be saying this all the time when we're doing the sum or difference of cosine and sine, but cosine is cosine, cosine, sine, sine. You just have to remember that it's the opposite sign in between those than what you were looking at. So this was a difference of two angles, so we have a plus here. This is a sum of two angles, so I'm going to have a minus here. So cosine of alpha plus beta is cosine alpha, cosine beta, cosine, cosine. Opposite sign minus sine alpha, sine beta. Okay, so let's say we have 2 points on the unit circle. So let P and Q be 2 points. On the unit circle. So let's say P is located at angle alpha, and Q is located at angle beta. And because we want to just be between 0 and 2 pi, we know that this can occur other places, but for now, let's just bound it between 0 and 2 pi. So let's say 0 is less than or equal to, and I'm just going to say that alpha is, so let's do beta smaller. Beta smaller than alpha. And that has to be between 2 pi. Okay, so I'm just going to arbitrarily choose 2 points on the unit circle. So let's just make our unit circle. And so we said that alpha was bigger. So let's say that this was where we got to alpha. So this point, like we were saying, this point can be defined as the x value is cosine alpha and the y value is sine alpha. And then let's draw a point where the angle is smaller. So let's say maybe this is angle beta. So this right here, this point right here, this is going to be cosine beta, sine beta. Okay, so let's form a triangle with these two angles with the both terminal sides. Let's see. Where do I want? And then let's do this. So this angle right in here, we know that this measure in here, well, if you looked at this right here, this is a whole thing to get to this side was alpha. And if we subtracted off this piece beta, that would just give us that center piece in here. That would be the angle alpha minus the angle beta would give us the angle in between forming that triangle. Okay, so now we're going to take this triangle, and it doesn't matter, right? The sides don't change. If I rotate a triangle, right? If I have a triangle and I rotate it, my sides aren't going to change. So let's just rotate this triangle so that this terminal side of angle beta, instead of lying there, it's lying here on our standard position, where we start our angle normally. And so if we kind of just rotated that around, so now I have my triangle where this side has just come down in here, and this side has rotated. I don't know, like this. So this angle, when we rotated it, it didn't change the angle. So this angle right in here, we could still say is alpha minus beta. So if that angle is alpha minus beta, then this point that we rotated, let's rewrite it in terms of that angle. So this point on the unit circle is going to be cosine alpha minus beta is my x value at that point, and my y value at that point is sine alpha minus beta. And the side now that is lying at that standard position, well, that point, that's just x is 1 here and y is 0. Okay, so let's look at this distance here. Actually, no, it's not. Okay, so I'm really only worried about the angle. I did rotate that triangle. So let's form a right triangle because we need a right triangle right now in order to deal with this. I'm stuck. Now I'm going to use the distance formula. Okay, let's look at this distance between these 2 points. So let's look at this distance in here. So distance between 2 points. Sorry, this is the change in your x value, quantity squared. So if I look at this x value, 1, minus cosine of alpha minus beta, that is quantity squared, plus it's the different distance of our y value, quantity squared. So this is, our y value here is 0 minus sine of alpha minus beta, quantity squared.
Is that a distance formula? Like how'd you combine that?
Yeah, that is a distance formula. Basically, if we're trying to find, and we can do this with using the Pythagorean theorem, and we made this right triangle right in here, and we wanted to find, let's say, this distance in here. This distance in here, right, this is our x value. And so our x value right here is 1, and the x value where this black piece is, that was where this point was. So this is cosine of alpha minus beta. And so this here, this distance of this piece of my triangle is 1 minus this piece in here, cosine of alpha minus beta. this distance right in here, this is this is my y value. My y value, the bigger piece, is sine of alpha minus beta. Minus the bottom piece, which is 0. So I really don't need that piece in there. So that was this piece. Sorry, 1 minus cosine minus beta, this would give me, and which makes more sense to me. Okay, it's all falling now to piece. It's all coming together where I was missing this piece. This piece right here, this is my 1 minus this would give me this. Okay. And so if I'm looking at this distance in here, this is the Pythagorean theorem. And so I'm looking at my hypotenuse, which this is right now, because it's across. That square root is equal to this distance squared plus this distance squared, our legs squared. Okay, so distribute that out. Okay, I got it. Okay, if we distribute this out, sorry, it's been a little while since I proved this and I thought I remembered all the steps. If we distribute this out, we have 1 minus cosine of alpha minus beta times 1 minus cosine of alpha minus beta. I distribute that out, I get 1 minus, my two middle terms are going to be negative 2 cosine of alpha minus beta when I combine them. And then my minus cosine of alpha minus beta times minus cosine of alpha minus beta, that gives me a plus cosine of alpha minus beta, quantity squared. So I can put the square here. And then if I do this right here, negative sine of alpha minus beta times negative sine of alpha minus beta, that's a positive sine of alpha minus beta, quantity squared. Okay, the whole thing is that right there, when I rotated this triangle, that side did not change, right? This side and this side, when I rotated it, is the same length. And so we can apply the distance formula for this first triangle. So if I look at the distance for this first triangle here, so by the distance formula, this is equal to the square root of the change in your x value. So cosine beta minus sine, or cosine alpha, quantity squared, plus then the change in your y value, sine of beta minus sine of alpha, quantity squared. So we're trying to prove what cosine of alpha minus beta is. If you look at this, we can set this equation, which we just found for that distance formula, equal to the same, this is equal to the same distance as when we rotated the triangle of this. And our whole goal is to get this cosine of alpha minus beta by itself. So let's use some stuff to simplify. I noticed that cosine squared plus sine squared, if it's the same angle, that's just 1. So we're going to use that fact. And then, so underneath my radical, for that first distance we looked at, we have 1 plus 1 in here. And so underneath that radical, we have a square root of 2 minus 2 cosine of beta. Cosine of alpha minus beta. Unfortunately, we need to distribute this out, but once we've distributed things out, things are going to combine nicely. Again, that we can combine things to rewrite them as 1. And so if we distribute this distance up here, we have the square root. Well, cosine beta times cosine beta, that's a cosine squared beta. Then our middle term is going to be a minus cosine beta times cosine alpha, minus cosine beta cosine alpha. So that's minus 2 cosine beta cosine alpha. It doesn't matter the order. And then we have a negative cosine alpha times a negative cosine alpha is a plus cosine squared alpha. So unfortunately, this is really, you need a lot of room. So if you FOIL out sine beta minus sine alpha, well, sine beta times sine beta is sine squared beta. We're going to get, our middle term is actually negative 2 sine alpha sine beta. And then a negative sine alpha times a negative sine alpha is a positive sine squared alpha. So notice that you're going to have multiple things with 1 in here. We have a cosine squared beta. Look for the sine squared beta, which is right here. So this sums to be a 1. And then let's see, we have a sine squared alpha and a cosine squared alpha. So this also sums to be 1. And then nothing cancels or nothing or like terms with this negative cosine beta cosine alpha and the negative 2 sine alpha sine beta. So let's just rewrite that, clean it up. So this is equal to the square root of 1 plus 1, so 2. And then we have a minus 2 cosine. I'm going to write it alpha first and then beta, cosine alpha, cosine beta. And then I'm going to have minus 2 sine alpha, sine beta. Okay, so like I said, those two sides were identical. We just rotated our triangle. And so we can actually set these two equations equal to each other. And let's square both sides. So maybe let's call this d sub 1 and d sub 2, just so I don't have to rewrite the whole thing out. So d sub 1 equals d sub 2, right? Well, if that's true, then if I square both sides of my equation, that also has to be a true statement. So then d sub 1 squared equals d sub 2 squared. I wanted to do that so I didn't have to rewrite this, and I can just get rid of my radical now. So if I square my d sub 1 side, that square root goes away, and I'm left with 2 minus 2 cosine of alpha minus beta is equal to, I squared d sub 2, so that radical goes away. 2 minus 2 cosine of alpha, cosine of beta, minus 2 sine alpha, sine beta. Almost there. Notice if you subtract your constant of 2 on both sides, that goes away. And notice we can get rid of the negative 2 in front of our cosine alpha minus beta, which is what we're trying to show that formula works, by dividing all terms by negative 2. And we can do this because this is an equation. So my left-hand side, we're left with cosine of the angle alpha minus beta is equal to, well, negative and negative, those cancel. Cosine of alpha, cosine of beta. And then negative 2 over negative 2, those cancel, making this plus sine alpha, sine beta. And so we showed what we wanted to show. And I want you to, I'm not going to give you any points if you do this. I just want you to see, when we've been doing these trig functions of angles, they're functions. You can't distribute a function to angles. This does not, and a lot of times students want to do this, and it would make our life easy if this was a true statement. But cosine of alpha minus beta, this does not equal cosine of alpha minus cosine of beta. So if you did something like that on the test, you wouldn't get any or very little partial credit. Okay, so that was kind of a long proof, or showing the reasoning why we can use this formula. This formula, the other ones actually aren't too bad, because we can use other identities that we know to prove it. So for instance, we can now use this because we just proved it. What if we rewrote this? So what if we were trying to prove cosine of alpha plus beta? Well, we know what cosine of alpha minus beta is, so let's just rewrite this a little bit. And so we can rewrite a plus as a minus and negative. And so we could rewrite this as cosine of alpha minus a negative beta. Okay, so we can now use our formula. So difference of angles for cosine, so that's cosine of the first, cosine of the second. So cosine alpha, cosine of the second is negative beta, plus sine of the first, sine alpha, sine of the second, negative beta. Okay, so now we want to use the fact of even and odd functions. Well, cosine of negative beta, that's just the same as cosine of the positive of that angle. So that we could rewrite as cosine of beta down here. So that's the same thing as cosine alpha, cosine beta. And then sine of negative beta, this is an odd function, so we can rewrite it, bringing the minus out front. So this is minus sine alpha, sine beta. So this is our formula for the addition. Which was so much easier to do than drawing that picture and finding distances and stuff like that. And so I won't do it now, but the sine could be done with using the fact that sine and cosine are co-function of one another, right? So one is 90 degrees minus the other. And if we have 90 minus, then we can use that fact. Okay, so I know I have, just want to show you really quickly. So we can now use this to help us identify angles that we normally would not know. So for instance, if you had sine of 105 degrees, well, that's not a special angle. If you formed this with, wrote your angle, this is 105. And so our reference angle, what would that be? That would be 85 degrees. That's not one we know. But now we can manipulate this. Actually, we don't know cosine. Let me just change this to cosine. We can manipulate this into angles we do know. We know 45 degrees and we know 60 degrees. And 105 can be rewritten in terms of 45 and 60. So this is the same thing as cosine of 45 degrees plus 60 degrees. Order doesn't matter. And now, without a calculator, we can get the exact answer. So we can use our formula. So this says it's cosine, cosine, opposite sine minus. So cosine 45, cosine 60, opposite minus sine 45, sine 60. Okay, so 45 degrees, cosine is root 2 over 2. So this is root 2 over 2. All times cosine of 60 is 1/2. Minus sine of 45, root 2 over 2, times sine of 60, which is root 3 over 2. So this is root 2 all over 4 minus rules of radicals, both positive underneath, same index, we can multiply underneath. Square root of 2 times square root of 3 is square root of 6, all over 2 times 2, which is 4. We already have a common denominator. So when they ask for the exact form, and this is what I would ask for on the exam without a calculator. And so again, there's going to be at least one portion, most of it that you can do on this exam without calculator. Or I would create it that you could. Okay, so that was just the start of 8.5. So we'll go through and we'll show sine tomorrow and we'll do some more examples. But I just wanted to get through at least one example so you can see why knowing the sum or difference could be helpful for us.